Hi everyone. Some technical difficulties at the beginning, possibly. Please bear with me. Not sure if it's actually recording or not. Okay, sorry, here we go. This should work. Okay, so that was just some connection issues. And here we go. So sorry for that. Okay, so today we're doing a Mechanics 2 paper. This is from the summer of 2014, A2 Maths. Right, so first question. Now this is a fairly simple parabolic motion question. So you've got some particle and you're firing it out of, throwing it or firing out of a cannon or whatever. And the motion it's going to follow is always going to be this parabolic path, right? Before it hits the ground. Now the important thing about this is that you can treat the x and y components of its travel completely separately. You know that in this very simple scenario, the only force that's acting on the particle is the gravitational motion downwards force of gravity, which is mg. So the only acceleration it's going to experience is g, downwards. Now, we can use the constant acceleration equations for this, since g is the acceleration and it's constant. So we can use this idea that if you want the velocity at some later time, so v, and I'm going to just look at the velocity in the y direction, vy. So vy as a function of time is going to be equal to vy at time 0 minus 1/2, sorry, not 1/2, minus, that's for the distance traveled, minus gt. So whatever it is at 0, it gets sort of eaten away by the deceleration, and then you get the current velocity. So what is vy of 0? Well, we know, because we know that it is fired with a sort of net velocity of v is equal to 12. And this is basically the hypotenuse of a force triangle, of a velocity triangle, where this is the vx, which must be equal to, if this is theta, the angle of projection, then this vx is equal to v cosine theta, and this vy is equal to v sine theta. And so you resolve it along that. You just look at the y component for this question. So this is going to be v sine theta minus gt. And now I'm going to use this general expression to look at the velocity when I'm right at the top of the arc. Well, my y velocity, remember we're just dealing with the y velocity. At the very top of the arc, the y velocity is 0. It sort of slows down, is instantaneously at rest, and then starts accelerating downwards. So at the peak, vy is equal to 0, which is equal to yeah, so this is vy at t divided by 2, or t prime, where t prime is this number. So if it takes 1.6 seconds to do the whole thing, it spends half the time going up and half the time going down. So the time that it's at the top must be halfway through, right? So this is t over 2, and that's equal to v sine theta minus gt over 2. So that's 12 sine theta minus g 1.6 over 2, and that's equal to 0, and you can solve for theta, no problem. Okay, so this one is all about resolving forces and friction, and it's actually it's a fairly tricky one. The biggest reason being that you have so many different possible choices of axes. So, for instance, we've got our axes on the page, right, and the axis of the wall, which makes sense to be sort of y and x like that, right? But you also have this ladder, which is making an angle of theta. And it would make sense to talk about x prime and y prime, the sort of axes that are along the ladder or the rod. But then you've also got this weird 10 Newton one, which is not along any of those axes. So where are you resolving the forces? Like, what set of coordinates are you using to compare stuff? So as usual, the best set of coordinates is along the rod for this first question. But we're given the angle that the rod makes with this vertical and the angle that the 10 newtons makes with the vertical. So we don't have the angle that the 10 newtons makes with the rod. So what we're going to do, I mean, we do, but you can, okay, so there's a couple of ways to do this. You might like to just work out this angle, right? And you know that this is going to be theta minus 30 degrees. And then you can use that to sort of resolve all. So let's do it that way first, and then I'll show you the other way. So if we do that, we're going to say that let's go into the rod's reference frame. So let's imagine that we've rotated our heads, and now the rod is lying like this. So it's got this 6 Newton force going down from its weight, and then over here, it's got an upward component of 10 sine theta minus 30, which is this one, right? So this force can be resolved along the rod like so and like so if you work out what this angle is. The other alternative, which might be easier for some people, is to first take this 10 Newton force, resolve it along the page's axis, so the straight up vertical, like the wall up. Is 10. And then imagine that you just have that guy and that guy, which is equivalent to the 10 Newton guy, right? Sorry for the messiness. And then take these and resolve them along the rod. So this is another way, but then you have to sort of, then you account for the fact that that is theta and that is theta, and you resolve again along the rod, or you can do it in one. So these are two possible ways to do it. So the first question is asking you for the value of theta. And what they want you to do is use the fact that this system is at equilibrium, i.e. it's not moving. I'm just going to get rid of some of this stuff so we can look at it properly. This rod is not moving. And it's neither like shifting around nor is it rotating. And they want you to use that fact to say that the net moment around any point, so for example A, is 0. So there's no net moment around A. It's not, otherwise the rod would be rotating around A. So we look and we think, what forces are acting on the rod? Well, it's these guys, right? So that's A. And we don't care about anything that's going on at A. That's why I chose A, actually, because if you look at A, you have to deal with the reaction force coming out and the force of friction, and which actually might not even be going that way. It might be going down, who knows? Force of friction, question mark. But if you use that as the center of where your moments are being evaluated, excuse me. Excuse me, still got a that is actually being applied at that point, because you can't have any moment or torque that's being inflicted on a point if it's being applied directly to that point. You can't rotate something by just pushing down on it directly. You've got to sort of use a lever. You've got to have some distance, So I don't care about A. These are my only two forces that I care about. So, and I know that they must be balanced. The moments must be balanced. So the moments are, so what's the distance from 0 to 6n? Well, that's 0.8 meters. And the whole distance, next to the end, is 1.2 meters. So the net moment around A is going to be equal to 0.8 times minus, because they're acting in opposite directions, right? Like if either of these was to rotate around A, they would be this one would be rotating, and this one would be rotating clockwise. So there's a negative sign between them. So minus 10 sine of theta minus 30. And you can solve that, and that's equal to, which is equal to 0. And you can use that to get theta. Okay. Oh yeah, and just, you have the double angle formula in your booklet, so you can use that, or you can just sort of rearrange the calculator and then remember just to add 30 afterwards, because it's theta minus 30. Okay, so now they want the coefficient of friction between the rod and the wall. So let's look at what's happening at that point. So here's our point A. There's the rod leading down like that. And the forces that are going on. Well, we know that this rod must be exerting, whatever's going on with the rod, it's exerting some force in there. And there is some force acting like this. And this is basically what's coming from what's happening at the end of the rod. So there's your 6 Newton force here is that one, and this way component, the x component of the 10 Newton force, which is 10 sine of 30. And remember, now we're looking at the up and down page axis, not the axis along the rod. So it's 10 sine 30 degrees is the x component here of the 10 Newton force. So what must we have? Well, we must have a reaction force, and we must have a friction force. Now we don't know which way the friction force is going to go until we've worked out where the motion is sort of going without the friction force, if you know what I mean, because friction always opposes motion. So you don't know if this rod wants to move up or down the wall, so you don't know which way the friction. Oh yeah, oops, forgot to add in the y component of the 10 Newton force. That's 10 cosine of 30 degrees. So the net force before friction is 10 cosine of 30 minus 6. And you will see that this is greater than 0. So therefore, the net force is moving the thing upwards. So the force of friction is therefore downwards. So we have an additional force going down here, which is the force of friction. And we know that from our formula that, which you should memorize, that F of force of friction is mu times R, where R is the reaction force. Which must be, this thing is in equilibrium, so it must exactly cancel this thing. So it's equal to, it's the same as that. And we know the reaction force because it's got to be the same as that, the force into the wall. And therefore we just divide that by that and we get mu. And you should get mu is equal to about 0.532. Okay, so elastic strings. The sort of king equation for these questions is tension in an elastic string is lambda x over L, this is in your formula booklet. So lambda is the modulus of elasticity of the string. L is the natural length, and x is the sort of amount that it's been distorted beyond its natural length. Not the full length of the stretched string, but just the amount after the natural length. So in this first question, we have to use it. And we're told that this is the situation. We have some point O, and then we have a string hanging, and then some ball. And we're told it's hanging in equilibrium. So the natural length. So what are the forces on the string? On the ball? Well, there's the mg, and there's the tension in the string. So mg must be equal, and that in turn is equal to lambda x over L. And then you can just solve for x in terms of the things that we already know. So it's Lmg over lambda. We have the natural length of the string, 0.8. We have the mass of the particle, 0.4. We know g, and we know the modulus of elasticity. So that gives us x is equal to 0.2 meters as required. So now we're moving into a different scenario. They are that you give the particle a sort of punch downwards, some sort of impulse, and it heads down at some speed. So we're looking at a later time now when it first comes to instantaneous rest. So this is a familiar elastic thing. You push the thing, it distorts, the elastic stretches. At some point it stops stretching and starts heading back, and that's the point of instantaneous rest, where it's sort of momentarily still, when it stops decelerating and starts accelerating the other way, which is, I guess, the same thing. So here we are at O, and originally like so, where that's 0.2, that was the natural length 0.8. So this is when we were hanging, and at some later time, we're all like this. And we know that it's 1.4 meters is the full thing. So again, let's say that's 0.8, and this is now 0.6. So where did I get that from? Well, the whole thing is 1.4, and I know the natural length is 0.8, so the new amount that it was stretched is 0.6. And now it becomes a conservation of energy question, because you have loads of different types of energy. You have kinetic energy, so kinetic energy, potential energy, which is called V, and of the potential energy, this is both V elastic, so the elastic potential energy of the string, and gravitational potential energy. So at the very beginning, well, we've got 1/2 mv squared, because it's just about, it's moving. And we have the elastic potential energy. So for this, you may or may not know, but the elastic potential energy is 1/2 lambda over L x squared, where x again is the amount that's been stretched. So here we've got 1/2 lambda over L x naught squared, so meaning x naught is equal to x naught. And we also have some gravitational potential energy from being above where it ends up, and that's going to be 0. Because here it was 1.4 and here it was 1, so it must be 0.4. So plus mgh, which is the expression for gravitational potential energy, is equal to, well, at the end, it's an instantaneous rest, so there's no kinetic energy. So you just have the elastic potential energy. So again, that's lambda over L, and then x prime squared, where x prime is the amount that it's stretched now, which was here was 0.6. Plus, well, there's no gravitational potential energy either because it's right at the bottom. So you got this expression, and you can solve. So this is V naught over there. So when it's first moving, it's moving at V naught, and at the end, it's not moving at all. So you can solve this for V naught because we've got M, we've got L, we've got lambda, we've got X naught, we've got M, G, and H, we've got X prime. So we have everything in here. And use this to solve for naught. Now the third question is pretty much exactly the same deal. So now that we're going to a third scenario, now we're at a point where the string has done all this, it's come right to the end, then it's bounced back. So first it was up here, now then it was sent downwards all the way there, now it's bounced all the way back up to the point where the string becomes slack. Well, when is the string slack? The string is slack when x is 0, when there's no distortion, as in the length of the string is its natural length. So it's got to be 0.8 above O. That's just hanging at its natural length. Now, it's not just hanging there in equilibrium. This is the point where it's sort of gone down to the bottom and then head up, and maybe it passes through this point on its way, and it probably is going to bounce around a few more times before setting towards equilibrium here. But this is just at a point, so it's still moving. It's still moving upwards at this point. We've frozen time, and we're asking what speed is it moving? So it's exactly the same thing, conservation of energy. So we know that when it was right at the bottom, this was its potential energy. So we're going from here to here. And energy is always conserved. So the energy of this whole system when it's like this is the same as when it's like this. So 1/2 lambda over L x prime squared is equal to 1/2 m v prime or v squared, whatever this v is that we're looking for. And we've also gained some potential energy. So how much potential energy have we gained? Well, it's risen 0.6 meters, right? Because at the very base it was at 1.4, and now it's at 0.8, so it must have risen 0.6 meters. And that's all you need. We have lambda, we have L, we have x prime, we have M, we have G, and we have H. So you can solve for V pretty easily. Okay, I've just realized that the broadcast has malfunctioned. So I don't know when that occurred. I'm just gonna check, okay? Bear with me. So now it's back, but when did it go off? Let's find out. Right, so it went off when we were still like a question ago. I went off for quite a while. Okay, so I'm gonna redo this one because I feel like it was down for so long. Yeah, that's down for about 9 minutes. Well, okay, well, let me just let me go back to the point where it went down and sort of do a quick review. I mean, you've got the audio from before, so really sorry for this. And we'll see. So the video went down around about here, so about a question ago. So I think we covered this all right. The entire thing where it was black was this question. I need to just check more often that it hasn't gone down. So here are all the various drawings that I made while doing this question. The important facts that I emphasized was this equation, which is in the formula booklet, and this idea of just plotting out the different scenarios that getting the different measurements at each point and realizing what's going on in the dynamical system. So again, let me just go over quickly. So showing that the extension of the string is 0.2 meters, that was very easy. You just take this equation, recognize that when it's in equilibrium, all the forces are balanced. Therefore, the tension must be equal to the gravitational, equal to the weight, mg. And then plugging that in here and solving for x because we know everything else. Now, the second part was a conservation of energy equation, and it was looking for the difference between these two scenarios. Calculate the speed at which P is projected. Well, at the beginning, you have the kinetic energy, and you have elastic potential energy, and you have gravitational potential energy. And at the end, between these two scenarios, you only have elastic potential energy because it stopped moving and it's at the very bottom of its run. So you've lost that, and this contained stuff we already knew except for V0, which is what we had to find. So that was simple enough. And exactly the same thing happened with the second part. So here was the kinetic energy at the end, the gravitational energy at the end, and that was equal to the elastic energy at the beginning. And you could easily solve for that. So I really hope that it's okay for you to just sort of go back and listen to that while looking at these notes, and I hope this was helpful. If you would like me to go over it again, please ask in the forums. I'm really sorry about that. Okay, question 4. So this one's not too bad at all. It's one of these parabolic motion equations again. So you're projecting some particle at an angle. So it's being shot out of a cannon, like so. And it will follow there is so this is even more simple than I realized. Okay, so there's no air resistance, there's no nothing. It goes up and it comes down again, like everything does. And you're asked, you see, it's a parabola, right? So this is like the y value, and this is time. So this also looks like the path that it would take if it was y versus x, the actual physical path in space. But you can also think of it as the height that the thing obtains as a function of time, and it also looks like a parabola. And it would look like that even if it was shot straight up into the air and then came down. It would still, even though in spatial space, velocity, initial velocity times time, minus 1/2 g times squared. Well, that's just the equation of a sort of frowny face parabola, right? Minus t squared. So they're asking, find the height of p above the ground, so the value of y, when p has the speed 18 meters. Well, what is the speed, the velocity? It is the gradient of the position. It is dy dt, right? So let's just work that out. That's going to be v0 minus gt. And you may recognize this from your constant acceleration equations as vy of t, right? That is just the expression for velocity at a given time. And that is the gradient they're looking for the height when the velocity is, say, 18. Oh, that's not so there's some height here, h, where the gradient dy dt is equal to 18 meters per second. And all you have to do is plug in V0 minus gt is equal to 18. This gives you t, and then you plug it back into y of t. So you have y of t, and that will give you the height, which is 3.8 meters. So you know that this is equal to 3.8 meters. Now you use this information to calculate the length of time for which the speed of p is less than 18 meters per second. So it's talking about the speed of p, not the height of p. Well, where is the speed of p less? Where is the gradient less than 18? Well, we know that the gradient is 18 at this spot, and it must therefore be sort of negative 18 and the mirror image on the other side as it starts heading downwards. So the period for which it is less, for which it is shallow, is this bit here. Well, that's really easy for us to work out. We can work out the time for which it reaches this, like t1 and t2. So we can okay. So the point is that we worked out a time here. At this initial time, the velocity was plus 18 meters per second, like 80 meters per second upwards. This is question 1. And I think that time was something like 0.34 seconds. So there's a couple of ways to do this. They've given you a lot of marks because what they expect you to do is take this equation, which is a quadratic, solve it as a quadratic equation for the time for which this thing is equal to 3.8 meters. You could just be a little bit clever and realize that this whole thing is symmetric. So if this took 0.34 seconds, actually, no, you can't be clever because you don't know how long the whole thing took. Never mind. Let's do it the way they want us to. So you've got that y is equal to v0t minus 1/2 get squared, and you've got to say that that is equal to 3.8 meters. So this is just a quadratic equation, right? And you will get two values for the time. You will get 0.34, and you will get 2.23. So those correspond to this T1 and T2. So therefore, the time delta T is just T2 minus T1. So this delta, it's the Greek capital delta. This refers to a change in something. The screen's gone off again. This is so annoying. I'm so sorry. Let's just see when that happened. Okay. So I'm seeing that happened quite a while ago. So let's just do this again. I wish it would tell me when it did that. So you see quite a lot has gone on. So let's just go over that quickly again. We were talking about this function, which is a parabola because it's got t squared, and the fact that its gradient changes as you move along, and it flattens out at the top and then starts sort of becoming more and more negative. And so that we could solve for the points where the gradient was equal to 18 by differentiating and setting to equal to 18. There's another way to do it, actually, now that I see this, is to use conservation of energy, in which case you could just go that 1/2 mv squared is equal to 1/2 mv prime squared plus mgh. And this is where this is the initial velocity. And this one is the 18. And you can solve for height that way. So that's actually, you know, like a quicker way to do it. But I think working out the derivative here is needed in the next part of the question anyway. So so why not? So we used okay. So let's review. We've got this height. We've got this 3.8. Now we want the length of time for which it spends basically above that height. Because if we look at the parabola, we see that at that time the gradient is a certain value. It only gets shallower from there. Then it starts sort of, its absolute value increases, but by which I mean it gets more and more negative, like steeper. But it's all shallow between those two times. So we're looking at the time that it's spent above that height. So if we look at the equation for height, which is this y, and we solve for time, and remember it's quadratic, so there are two solutions. We get time 1 and time 2, and we know that therefore the change in time is delta t. So that's what we did. And then we can finally turn to the equation for the x coordinate. X is a function of t. Well, this is just going to, there's no acceleration in the x direction. There's no force acting, there's no air resistance or anything like that. So x is going to be just Vx naught. When I say naught, you know, I mean like at time is equal to 0 times time and nothing. That's it. Well, what is Vx? Well, Vx is V naught cosine of 40 degrees. And here, V naught, this was y, the y coordinate of V naught, that was V naught sine of 40 degrees. So we have our x as a function of time. So therefore, the horizontal distance is just delta x, you know, change in x. And that's just going to be V naught cosine of 40 degrees delta t, where this was our delta t. So I hope that that's clear despite the blackout halfway through. I'm really sorry, guys. I really don't know why it's doing that. Okay, question 5. Yeah, I'm going to keep checking on, I'm going to try and like keep an eye on whether that thing is blacking out or not. So I'll try and drag it to one side of the screen so I can sort of see it. Okay, question 5. So this is a center of mass question. So the key formula is that m total times x center of mass, where this is a vector, right? So it's got an x and a y and a z component, however many dimensions you're working in, is equal to the sum over I mi xi. So how does this work in practice? Well, let's look at what we have. We can take some sort of complicated object and we can divide it into bits. So in fact, they've already said that it's a metal frame plus a rod. So we have this arc of metal and this rod, and we can just take their individual centers of mass and use this formula to work out where the center of mass of the entire object is. So what's the center of mass of the rod? Well, we know that if it's just a rod sounding like this, the center of mass is at the center. So that's the center of mass of the rod, no problem. So the center of mass of the rod, let's just be clear, is at 0, 0. Center of mass of the arc, well, that's a little more complicated. It's in the formula booklet. So if, so let's say, if the arc, so the way they put in the formula booklet is a bit obscure. So let me just, let me just formulate it this way. if an arc of wire, so we're talking about where there's a wire, not a disc, not like a half of a disc or any sort of segment. If an arc of wire is subtended by an angle 2 alpha, then the distance from the center of the full circle, so not the center of the arc, but you know, this center, this thing here, not somewhere here. Center of the full circle to the center of mass is R sine 2 alpha over alpha. 2 alpha. Yes, over alpha. Nope, that is not a 2 alpha in there. That's just alpha. Sorry. So I get confused. So here, this is just alpha. So the angle that is subtended by a semicircle is pi. That means that alpha is pi over 2. So this is the little subtlety. We're talking about something that's subtended by an angle 2 alpha. But in our case, 2 alpha is equal to pi. Therefore, alpha is equal to pi over 2. And this is in radians, right? Yeah, always remember these cases. Radians. So what does this mean for this equation? Well, that means that the distance is the radius sine pi over 2 all over pi over 2. Well, the sine of pi over 2, we look at it like that. That's pi over 2. So the sine of pi over 2 is 1. That's just 2 times the radius over pi. Well, that gives us just the distance from the center. But look, by symmetry, we know that the center of mass of just of the arc, it can't be off to the left or off to the right because this whole thing is symmetrical. So it basically just has to be 2r over pi up there, right? So center of mass of the x of the frame is 0 in the x direction and 2r over pi in the y direction. So now we pretty much have what we need. The only other things in this equation are the masses. So we're going to assume that everything has a unit mass. So like 1 meter of rod is 1 kilogram, and 1 meter of this wire is all the same material, so 1 kilogram. So we don't have to worry about the masses. We're just going to talk about the lengths, because the masses will just divide through anyway. If you see what in fact, you know what? For this very first question, I will be really rigorous and talk about the actual density, and then you'll see why we don't need to. What is m total? Well, that's going to be equal to the length of the rod, so that's 3.6 meters, times the density of the rod, because this is just the length. This has got to be, you know, kilograms per meter, plus the length of the wire arc. Well, that's just the sort of half the circumference of the circle, so that's pi r times the density rho. So this is and r is just 1.8. So this is 3.6 plus 1.8 pi rho. And remember, rho is density, which is, you know, kilograms per meter. Now the mass of And individually, the mass of the rod was 3.6 rho. Mass of the frame 1.8 pi rho. Full equation. Total mass 3.6 plus 1.8 pi rho x center of mass is equal to mass of the rod 3.6 rho times the x coordinates, the coordinate vector of the center of mass of the rod 0, 0. So that just disappears, plus 1.8 pi rho times 0 2r over pi, and 2r is just 3.6. Well, that we can, the rows will cancel because every term on both sides has a row in front of it. So the densities would always cancel. So we just don't have to worry about them. In fact, they the answers that they give don't even care about them at all. So you can just drop it and just treat length and later on area like it was all that mattered, that you didn't need any kind of density. So what do I get? Well, I get the x center of mass. And remember, with these vector equations, you can solve the x and the y coordinates separately. And we see that the y coordinates, well, this whole thing was 0. We don't need it at all. And there's no y coordinate here. So this is 0. And then the x coordinate, sorry, the x coordinate is 0. The y coordinate, well, we just divide by that thing, right? So we get 1.8 pi times 3.6 pi over pi over 3.6 plus 1.8 pi. And you can work that out. And you will get, oh, hello. So this is actually the next question. So what I was actually the center of mass of the whole thing. We've already worked out the center of mass of the frame. So that is damn. Right. No, the frame is the whole thing. Yes, no, the frame is the whole thing. I've been doing it right, sorry. So what I've been doing wrong is referring to the arc as the frame. So this should, oh, God's sake. I don't know why it does that. Oh, fuck's sake. Anyway, arc is equal to, so yeah, this should never have been frame. Arc. But the result is the same completely. So sorry about that. Okay, this video is full of apologies. So the distance to the center of mass from O is just the y coordinate of this thing because, you know, it's just up there. There is no x displacement. So it's going to be a little more further down than the than was the y coordinate of the center of mass of the arc, because the arc didn't have this rod sort of pulling some of the mass down towards the bottom. So it's going to be this, and that should be equal to 0.7 meters. Okay, question 2. So this is what they love to do with these, which is to say, okay, we're going to hang an object from some point, and it's going to hang in equilibrium, which an equilibrium, as always, means that the center of mass is directly below the point of suspension. So they're saying that we've got our frame and we're putting this lamina in the middle, and we're hanging it from A. And now remember, we're putting this lamina in, but that's not going to change the x coordinate of the center of mass because everything is still going to be symmetric in x. So it's only going to be the y coordinate that's going to change. So putting the lamina inside is going to shift the y coordinate somewhere, up or down. So it's just going to slide up or down this line. So it'll be somewhere here. And that thing is going to be directly above the point of suspension. You know, if I draw it correctly, it would be. And they're asking, what, if that's true, what is this angle here? So let's put this back on its front so we can deal with the quantities that we know. And so what we have is our center of mass, and then we have this line here, which is the vertical of that drawing, and then we have some angle theta. So we can immediately work out what this distance is here, right? The y center of mass, this angle, we have theta, and we know this distance, 1.8. So then we know that the y of the center of mass is just equal to 1.8 tan of 22 degrees, which is 0.7273. So you can see that it's, before we had 0.70, and now it's moved y. Obviously, it was 0 all the time. So m total, y coordinate of the center of mass, is equal to, so the mass of the frame times y frame plus mass of the lamina times y of the lamina, which is, you know, the mass of the frame, and then the y of the frame was 0.7, plus the mass of the lamina, which we're given, 27.5. And the formula booklet will again give you the equation for finding out the center of mass, or the distance from the center of mass of a lamina. So that gives us 2r, which, I mean, we know r, I'm just putting r for simplicity, sine of pi over 2, this time over 3 pi over 2, 3 alpha, r is 1.8. And we know the total mass, right? That's just the mass of the frame, or we don't know it, we know what it consists of, mass of the frame plus 27.5, y center of mass. We have the y center of mass. We, everything else is numbers, including this r here. So we can solve for the mass of the frame. You just got to remember that there's mass of the frame here and here. So you're going to have to, you know, do a little bit of manipulation. But you should get the mass, no problem. Okay, question 6. So this one is, again, a parabolic motion, or it's a vertical falling motion, but there's air resistance now. I mean, they haven't said it's air resistance, but when you get a some force which is proportional to the velocity of something, and if it's falling to the air, then, you know, it's probably air friction or air resistance. So this question relies, it's a differential equation sort of question. You've got to do some integration, and it relies on you having this little trail of reasoning that the force on an object is, you know, F equals ma, which is, you know, Newton's second law, and then expressing this as a derivative, m dv dt. And what is the force exerted on this object? Well, if it's falling, the only forces on it are the weight and this frictiony force, which obviously it's, you know, it's going downwards, so the friction force must be pointed upwards. So the force on the object is mg minus 3v. And now we want to make this into we want to separate variables, which is the the technique they always use in this in A2. dv. And by drag everything in v over to the left-hand side, I don't mean subtract. I mean you have to do it all by dividing and multiplying. It's no good otherwise. You need this as part of a single term. You need dv and all the v's as one term, and the same for the dt's. It's no good having several terms added together. So, and then I'm gonna, well, if I divide these things, maybe it'll be a bit more obvious what I'm doing. If I do this, that's equal to that. I've divided top and bottom by m. And then I'm going to say, actually, you know what? Instead of doing that, I'm going to times both top and bottom by dv over mg minus 3v. Now, why have I done this? I'm hoping it'll make it pop out a bit what this thing will integrate to. Well, it's again like what pops up time and time again is that the integral of f prime of x over f of x dx is the natural log of f of x. So if I differentiate this thing on the bottom, if this is my f of x, well, the derivative is just minus 3, and that's on the top. So that's why I multiply by these, by this pre-factors, just to make it obvious. Of course, that minus 2 would cancel with the minus a third. But let's just keep the minus m over 3 in the front. Natural log mg minus 3v. And let's talk limits. Well, what are my limits? What information do I have? I have that at some time is equal to 0, I've got some speed 1.95. And at some later time, I've got the speed v. So I want the distance. In fact, sorry, I've got the speed 0. So I want the final time to be the time that corresponds to when the velocity is 0, and the initial time to when the velocity is 1.95. So this thing just integrates to t. And when I'm going to say when v is 1.95, t is 0, and at some later time, it's t. And so you just plug this in. You go, mg minus 0 minus natural log of mg minus 3 times 1.95, and you work it all out. And don't worry about the negative signs; they will cancel. And this will give you t is equal to 0.738 seconds. Okay, great. Nope, I got the limits wrong because I was looking at the second question. I'm so sorry, guys. In my defense, I have got a bit of flu, so I really apologize. Wanted to get this out to you in time. So we're not looking at the second part. We're looking at the first part. Calculate the time after its release when p reaches the ground. So we're looking from time 0 to t, where 0 is the time when p has. So we're looking here. It's released, and then it accelerates to 1.95. So actually, the limits are the other way, 0, 5. So this is when it's heading downwards, accelerating downwards, just before it hits the ground from rest. The second one is about how far it travels, and for this one, like the limits will be as I said before. But let's just look at that. Let's just put this, make this a bit smaller, and I think we can get rid of those. Okay, question 2. So this is still a differential equation problem. So we're looking again at m dv dt. But now, what forces are acting on P? We've just given it this push, and now there is some opposing force. It's a smooth horizontal surface, which means that it's that there's no friction on the coming from the ground, but there is some sort of friction, which is this V. So it must be probably air friction. So this again is MA. So that must be equal to the force, and the force is minus 3V. Because we're talking about velocity being in that direction, and the force is acting in the opposite direction, so it must be minus. So it's got this directionality, right? Well, this doesn't look like it's got. It just looks like V's and T's. But we can use the dx dt, which is equal to, well, dx dt is just V, right? So this is equal to mv dv dx. And those things are equal. So that means that dv dx is equal to minus 3 over m. Well, this is much, much easier to work out, which is probably why it's worth fewer marks. So we've got dv is equal to the integral of dv. And here we were talking about the limits at minus 3 over m dx. Well, I want to talk about the point at which it starts moving as being x equal to 0, and the point at which it finishes moving as, some x, some distance. And at that time when x is equal to 0, what is the velocity? Well, it's 1.95. And at the time when it stops, what is the velocity? Well, it's 0 when it's at x prime. So v is equal to minus 3 over m. So within those limits. And that will solve to give you the right answer. Okay, question 7, last question. So we have a situation where particles move, it's on the end of the string. So this is a string. But it's also constrained to move around this wire. It's like a bead on a wire. Bead on wire. So what they're asking is about this thing called the contact force, which hasn't come up before. The contact force is also called the shear force. So it means a force exerted just by things being in contact. So we're talking about force exerted by the wire. And it's not, it's not going to be along, needs to be along any particular direction. It's not like the tension in the string where you've got this, very direct line of force and everything's, very clear. It's just about, it comes from friction and like various other things, electromagnetic repulsion, which I guess is friction anyway. So they're asking, what does it have to be to make sure that this thing is a physical scenario? And what they're saying is that the bead isn't moving up and down, right? The wire is stopping it from moving up and down. The contact forces of the wire. So therefore, everything must be balanced in the y direction. So we have our tension T, and we have our usual weight, mg. And now we're told that there's a contact force. And so let's work out what it has to be. So on our object, here's mg, here's t, and so that the t minus mg plus whatever the contact force is 0. The contact force in the y direction, so the vertical component, and this is ty, ty, not the whole t, obviously. Well, what is ty? We can get it from this triangle. Let's call this angle theta, as is usual, and we know that we can actually work out that for this triangle 0.3, 0.4, the hypotenuse is actually 0.5. That just comes from Pythagoras. and this is theta. Well, this is similar to this triangle with the forces, right, where the hypotenuse is t. And it's the same angle, theta. So therefore, we know that the cosine of theta is 0.6, 0.3 over 0.5, which is 0. And therefore, the vertical component of this guy, so that vertical component, is equal to t cosine theta, which is 0.6t. So we have 0.6t, and minus mg plus fc is equal to 0. And now all we need to know is t. Well, it's a wire, right? And it's an elastic string. So not the wire, so the string. And we're told its natural length and its modulus of elasticity. And we're told, well, we've worked out how long it is now that it's been stretched. So we know that the tension is lambda over L divided by 0.4, which is the natural length, times the extension, 0.4, and it's now stretched to 0.5, x must be equal to 0.1. So that gives us 10.5 m as the tension in the string. And that's all we need for this contact force equation. We have that the contact force is equal to mg minus, and mg is 10m minus 10.5 m, which is minus 0.5 m. And that means that it's acting upwards, because here we were defining 10m, we're defining the weight as acting downwards as being positive, and then subtracting whatever was acting upwards. So if what we end up with is negative, it means that the net thing must be upwards as well. And you can see that if I wrote them all out again, in this scenario, you would see that t is 10.5 minus 10 plus 0.5. So the contact force must be acting the same direction as t for this thing to equal to 0. So, oops, I made a mistake. This 0.5 should be multiplied by 0.6. Right, so there you go. So it's so you get 3.7 m. That makes sense. So that's not actually t, this is some other number, and that should be 3.7, and that should be, it's 60% of 10.5, which makes sense, because that's how we've set up the axes actually when we added them together. So they're it's got the same sign as t if it was on the same side. So as you can tell by looking at this, so it has to be acting upwards. Okay, so given that the contact force has 0 horizontal component, find the angular speed of B. Well, this is doing exactly the same thing, and it's really, it really won't take long. So you've got that so they're just telling you that the contact force has 0 horizontal component. It could have this horizontal component, they're telling you that it doesn't. So they want the angular speed. Well, in our scenario, what horizontal forces do we have? We only have the contact force of the wire plus the force of the tension. That's it. And since the contact force is in this sub-question has 0 horizontal component, the only one we have is t sine theta. So the x component of the net force is just equal to t sine theta. Well, that's equal to ma. And for circular motion, we use the fact that a is equal to v squared over r. So this is m v squared over r. And then we use the fact that v is equal to r omega. So this is equal to mr omega squared. Well, we've got t, we've got theta, we've got r, we've got m, so this gives us omega. Now, the third question is pretty much the same. It's exactly the same thing, in fact. I don't know why it's worth 3 marks. Now I've got fx net is equal to, now you've got t sine theta still there, nothing's changed. But now you have some sort of horizontal component coming from the contact force. But you don't know whether it's positive or negative, so you have to put a plus or minus. 2m is equal to mr omega squared. And then you just solve and you get 2 values of omega. Well, actually what they're asking for is the possible speeds. They're being very naughty and saying angular speed here, for which they mean omega. And then they're saying speed here, by which they mean v. So you know, it's in the solutions. That's very stupidly confusing of them. So let's use mv squared over r. So this gives you two possible values of v1 and v2, either plus or minus this 2m. So very last question. The string is now removed. So now we've got no string pulling from above. We've only got this motion in a wire with constant speed. And we're told that the vertical and horizontal components of the contact force have equal magnitudes. So we know that, so for this question, we know, and how do we know what these things equal? Well, we know, forget about the motion in a circle, right? We know that at any point, vertical motion is just influenced by mg and fy. The fy has nothing to do with the motion in a circle. You know, you can always resolve them across 2 independent axes. So therefore, fy must be equal to mg, and therefore, since fx is equal to mg, that's also equal to mg. And this is still equal to mv squared over r. So this will give you a value of v. And that is our lesson. I am, again, really, really sorry about the technical difficulties. I hope everything was clear and that you can get the introduction from how I went over it. Please, if you have any questions, go onto the Slack forums. I'm there to try and fix any misunderstandings that happened because of this technical difficulty. Okay, thanks a lot.